So yeah, thank you very much for the introduction. And I must say that I'm very grateful to the organizers for the invitation. It's been a fantastic conference. I must say it's my first online conference, and if online conferences can be that good, I think we're in danger of not going back fully normal when the pandemic permits. So today I'll talk about the diagrammatic Monte Carlo technique, and I'll try to explain that it's really a universal framework for addressing some of the most difficult problems in correlated many-body systems. And what I mean by what I mean by correlated loosely is that it's a situation when the kinetic energy is of the order of the interaction energy. I will call these strong correlations, and typically leads to collective behavior of particles. You cannot consider particles one by one, and leads to highly non-trivial physics. Well, what kind of physics? Well, we know that even in the case of very weak correlations, or relatively weak correlations, I should say, is already very important. In particular, understanding of semiconductors and the invention of the transistor in the middle of last century has enabled our today's discussion. What can strong correlations bring? I'm still learning how to use the whole thing. Okay. Well, we're already using some strong correlations, strongly correlated systems in practical applications. And if we're able to improve the figure of merit, for example, the superconducting critical temperature by a factor of 2 or so, then it's even difficult to imagine what kind of breakthroughs for technology that could bring, potentially enabling new means of energy storage, energy transmission, and even solid state base for quantum computers. So it's a very important task to try to understand and understand the mechanisms of strongly correlated systems, and what these mechanisms, what physics they can bring about in a quantitative way. And this has been a very difficult problem, essentially because there is no small parameter to build a reliable theory. And in this context, even the simplest model, the so-called Hubbard model, has been essentially unsolved for 50 years. We know much more about it now, but the model, the whole phase diagram, has not been uncovered. So I will use the Hubbard model for illustrations in this talk. So I will introduce it in some detail. So the model essentially consists of electrons of 2 types. Let's say spin up and spin down electrons, or fermions generally, hopping on the lattice with a hopping probability T. And whenever 2 electrons appear on the same site, they repel each other with the repulsion U. And the last term in the Hamiltonian is the chemical potential that controls the density. So essentially, there's 2 independent parameters, only 2 independent parameters in the model, and temperature is the third one. It's a very small configuration space. It seems like the model is even simplistic, but it turns out that the physics that it can harbor is very non-trivial. The model definitely exhibits ferromagnetism, antiferromagnetism, different types of incommensurate magnetic phases, stripe phases, and it is also speculated that it should show some different types of exotic non-ferroliquid behavior, possibly pneumatic phases, and of course the holy grail of the context of this model, the high temperature superconductivity, is expected to be captured by this model. Now, why calculating anything for a correlated system is difficult? We have quite powerful computers these days. Well, even if I look at the simplest example, it's quite the standard example if you heard talks on Monte Carlo methods. If you just consider the simplest correlated system, a system of spin 1/2, spins 1/2, let's say 10 by 10 lattice, then if you want to compute the partition function, just a sum like this, well, at some point in life, I estimated how long it would take. It was 4 million years a few years ago. Now it's probably less, but that's the order of magnitude. So it's a time scale that is not on the human lifetime time scale. However, it turns out that this problem of huge configuration space that you need to sum over for even such a small system can be quite straightforwardly solved by the so-called Monte Carlo method. And the idea is that instead of summing all terms one after the other, one can generate configurations stochastically with a probability proportional to the contribution to the sum. Okay, when we do this, we're essentially summing over the most relevant configurations first. So we're achieving essentially fast convergence of our results. And most importantly, we have control of accuracy. We know precisely what our error bar is from monitoring standard deviation of our answer as we accumulate it statistically. And we know that if we wait long enough, then we'll recover the exact answer eventually. But most importantly, if we're interested in the results with some reasonable accuracy, let's say a few % accuracy, then for this particular system, this could be done in a matter of seconds on the laptop. Right. So Monte Carlo has been huge across different fields of physics. But that was an example for a classical system. How can we simulate a quantum system? Well, it turns out it's not so different. If we recall that we can actually represent a quantum system as a sum of all possible classical trajectories after Feynman, and each trajectory enters the sum with some probability, W, and this trajectory in the world line space forms a configuration space, essentially, over which we can sum. And we immediately see that we can find answers such as the partition function for a quantum system as a sum of all possible trajectories in this world line space. And we're back to the original Monte Carlo setup. So we're back to the same formula we had for the spin 1/2 system, for the simple Ising model. And all we need to do is sample each contribution with the probability proportional to the weight. And this method has been extremely successful for bosonic system, known for straight and quantum systems. And such, however, for fermions, it's slightly less trivial. So what happens with fermions is that due to the Pauli principle, we know that whenever we exchange two particles places, the wave function must change sign. And therefore, for the trajectories, that translates to whenever two trajectories are interchanged, the weight of the configuration changes its sign. And therefore, when we compute the sum, these terms can have alternated signs. So you see, the idea of sampling with a probability now becomes a little problematic because we really don't know how we can sample with negative probabilities. The probability is by definition a positive definite quantity. So the Monte Carlo scheme must be modified. Well, how do we modify it? Well, most obviously, we will have to sample with the absolute value of this weight, right? And then a statistical average will become a formula like this, where the sign becomes part of the observation. So the final answer for the statistical average will be just the ratio of two terms, where you have the average sign of the configuration weight in the denominator. And it turns out you can easily demonstrate that this average sign goes to zero exponentially with the system size and the inverse temperature of the system. And you immediately see that this is a big problem, because your answer essentially becomes a ratio of small numbers. It's 0 divided by 0, where each term in the numerator and in the where the term in the numerator and the term in the denominator are known with finite error bars. Therefore, you have to make sure that the error bars are much smaller than the actual average, which itself becomes exponentially small. And that leads to exponential computational times in principle. This is known by the name of fermion sign problem. So in practice, what does it mean for a realistic calculation? Well, when we're simulating a piece of matter like this, in this way, we understand that well, we need to choose the size of the system, and the system size needs to be at least comparable to the correlation length that is dictated by the underpinning physics that we're looking for. And therefore, the sign which scales exponentially with the system size scales actually with the correlation length, and we see that the computational time therefore must be an exponential of the correlation length, which in many important regimes becomes just prohibitively long for any practical computation to be possible. And this is precisely the point where a diagrammatic Monte Carlo can step in, because the main feature of diagrammatic Monte Carlo is that it computes properties directly in the thermodynamic limit, in the limit of infinite system size. So in principle, there's no sign problem in this sense, in the canonical sense of quantum Monte Carlo methods. And it's actually possible to demonstrate that in many important cases, not always, but in many important cases, the computational time that is needed in diagrammatic Monte Carlo to achieve a desirable accuracy epsilon scales only polynomially with this epsilon. So in this sense, diagrammatic Monte Carlo solves the computational complexity problem of fermionic systems. Okay, so obviously diagrammatic Monte Carlo is based on Feynman diagrams. So let me just quickly remind you what these are. So typically we're facing a problem where we have an easy to solve part. We usually call it the non-interacting part, and the difficult part, the interaction part, but this definition is somewhat loose, as we'll see later on. But typically it's just well, at least for the cases I'm considering here, this term needs to be bilinear in fermionic operators, and the interaction is everything else that doesn't commute with this term. So you see that computing answers with this Hamiltonian is quite difficult. However, if I introduce this expansion parameter psi, and I can expand my answers with respect to the expansion parameter, and look for the answer as a series, while in the final answer I will always set psi equals to 0. So psi will be just a means of tracking the order of perturbation theory. And so the thermodynamic average will look something like this. It will be an expansion in the powers of psi. When I do it, it is very standard. The important point here is that in each of these terms, the average is easy to evaluate. So the statistical average is taken with the non-interacting part, which is easily solvable. So each term is easy to evaluate. And Feynman diagrams are just essentially a way of keeping track of all the terms and bookkeeping. So they're just a graphical way of representing the terms of the perturbation theory. And this is usually done in the following representation. We have what we call a non-interacting Green's function, which is a correlation function like this. It depends on times. It depends on momenta. And the average is taken with respect to the non-interacting Hamiltonian. So this function is known analytically. It's easy to compute. And to this function, there corresponds a line. Different colors correspond to different spins, and the line, which starts at some time tau1, ends at some other time tau2, and carries a momentum k. And the rules of constructing the perturbation expansion tell us that we need to connect all these lines to interaction vertices, which has a structure like this. It conserves momenta. And therefore, the resulting series is constructed by all ways of connecting these lines to vertices. And for example, for the fully interacting Green's function, it looks something like this, the first few terms. And the full Green's function essentially captures single particle properties of the system, including thermodynamic properties, dynamic properties. So it's a very important quantity to be able to compute. Gives a lot of information about the system. Right. And in these rules, it's important to note that we're doing integrals over all internal variables. So whenever we're connecting the lines, there are internal variables, the momenta and times at which the interactions happen, and we need to integrate over all those variables. So each of these terms is actually quite a big integral. Okay. However, I told you that the number of these diagrams grows with order combinatorially, because it's just it grows with different ways you could connect the lines, which is a combinatorial number. So it grows as a factorial, which means a few things. So the first thing we can immediately notice that is that the series is absolutely divergent. That is, if I take the absolute value of each term without the sign of each term, then I can easily see that no matter how small the interaction, okay, each term is proportional to the interaction to a certain power. This, for instance, this one would be interaction to the third power. So it's just has exponential scaling on the diagram order with the interaction. No matter how small it is, the number of these terms grows factorially. So a factorial eventually will beat the exponential, no matter how small the exponential, and therefore the series must diverge in the absolute sense. This is not very good news, but for fermions, we're actually saved by what the founding fathers of diagrammatic Monte Carlo call sign blessing, right? And it's the fact that the alternation of sign of diagrams that converge, diverge in the absolute sense can actually lead to cancellation of n factorial terms at high orders, and therefore to convergence of the series. So actually for fermions, the series is not meaningless at all. And another observation is that the series is very quickly becoming impossible to evaluate with basic analytic means, even with Mathematica or numerical integration. If we just integrate, if we just compute each term individually, we're quickly out of our ability to evaluate the series just within the first few orders. But we see that it's very similar to the problems we saw before, where we're dealing with a huge configuration space, and this is where Monte Carlo methods have been very efficient. So the idea of diagrammatic Monte Carlo is, why don't we use Monte Carlo sampling instead of evaluating these diagrams term by term to obtain the answer. So this is how, in principle, diagrammatic Monte Carlo works, as was originally introduced by Prokofiev and Swistunov two decades ago. And the underlying fundamental idea is that let us well, Monte Carlo is based on the concept of configuration weight, a configuration space. So let's consider the diagram order, the diagram topology, and all internal variables as our configuration space, axis and configuration space, and each particular integrand in the series will be a point in this configuration space. Then, by the same rules as for the simple Ising model, in principle, we can sample this configuration space with probability proportional to the weight of each integrand, to the contribution of each integrand to the whole series. Right? This is the idea, and in reality, I will mention an example. We typically these days use deterministic summation over topologies and stochastic sampling over all other variables to take advantage of some of the sign blessing, of some of the cancellations. Not all of it, because the sign also changes as we change the internal variables of integration, but some of the sign blessing could be taken into account already at the level of generating the weight of each configuration. Okay. And an important point to mention at this point that the series is still absolutely divergent, so it is unavoidable that we have to introduce a cutoff of this Monte Carlo sampling, because the Monte Carlo sampling also only knows about the absolute values of the weight. And so inevitably, if we let Monte Carlo explore very high orders, it will go to infinite orders, because this is where the configuration space is the biggest. So we have to enforce a cutoff on the diagram order. And this is the main limitation, practical limitation of diagrammatic Monte Carlo. And I will demonstrate how that translates to controlling the accuracy. So I can, at this point, summarize the diagrammatic Monte Carlo framework. So basically, diagrammatic Monte Carlo computes coefficients, these coefficients an, in an expansion with respect to some expansion parameter. It could be the Bayer coupling. It could be just an auxiliary parameter xi. We'll see. It's actually up to us. It computes the coefficient of this expansion of some thermodynamic observable in the thermodynamic limit. Right? So that's an important point, that all these diagrams are formulated in the thermodynamic limit. And the framework requires three fundamental ingredients for it to work. So the first one is the choice of diagrammatic representation. And this is where we truly have a continuum of possibilities of what series to actually simulate. And always the choice is motivated by improving convergence properties of the series. But we can do we can use all the tricks and all the techniques of 1960s, which you can find in this Bible of quantum field theory and many body physics. The use of all sorts of renormalizations, dressing the propagators with different diagrams, specific topologies, or all topologies self-consistently, skeleton series. So all those tricks that we know from analytic diagrammatic theory, we can use in diagrammatic Monte Carlo in the same way. That's a major advantage. But there's actually more tricks. We can we can change the starting Hamiltonian around which we expand in a very wide class of Hamiltonians, and we saw some examples in a talk by Felix, and we'll see some in the talk by Kuhn tomorrow, I believe. Yes, and moreover, I will give an example of the shifted action, a very simple example in this talk. But more generally, we can start with a continuously transformed action, as was explained by Boris in his talk yesterday, where the general idea is that loosely we can deform the action with some continuous parameter w however we please, with the key requirement that at some specific value, let's call it w equals 1, the action recovers the original action. And it turns out that this flexibility can give us a lot of additional tools to control series properties. In particular, Boris demonstrated yesterday that you can start with a model which has 0 convergence radius due to the famous Dyson collapse argument, and you can regularize it by homotopic action and write down an action which will be identical to the original action at w equals 1, but which would have a finite non-zero convergence radius, which is a major improvement. I will refer to Boris's talk for more detail. Now, the second ingredient is, of course, the algorithm we use for computing these coefficients. And the algorithm depends clearly on the type of the expansion. And we have already seen 2 examples in the talks by Felix and Chris, and there will be another one discussed by Kuhn, I believe, tomorrow. And the final ingredient is that once we have computed these coefficients, and like I said, we're naturally limited by a finite number of terms, we somehow must extract the answer from the series, knowing only the finite number of series coefficients. And that, of course, depends on the convergence properties of the series. And but the bottom line is that controlled results could be obtained even with divergent series. And we had already an example of this in the talk by Chris. So divergence is actually not the end of the game. Oftentimes we can find. Hello, sorry. Zoom was telling me that I was lost for a minute. So in many cases we can find controlled results even from divergent series. So how does it work in practice? So I'll go back to the Hubbard model, and I will illustrate it by an example. So I start with, so the first one, the choice of the expansion. So I will start with the simplest shifted action. In fact, it's so simple that it could be done at the level of Hamiltonian. You don't need to worry about the action. The idea is very simple. It's been known since the 60s. In fact, I can add a term, this term proportional with alpha, to the Hamiltonian, and I can subtract it. But whatever I've added, I will associate with my non-perturbed Hamiltonian, H0, and whatever I've subtracted, I will include in the interaction. Okay, so this will be my combined interaction term, and clearly I recover the original Hamiltonian psi equals 1, but now I have a free parameter alpha, which I can tune to improve properties of the series. Obviously, the expansion will be very different for different values of alpha. Now, the second ingredient is the algorithm. So I need to choose the algorithm, and in the regime of interest, the most efficient one so far is the determinantal diagrammatic Monte Carlo algorithm, called CDAD for short. And the idea is that the series coefficient, if I spell it out in terms of diagrams, it looks like this. And if I fix all the positions of the vertices before I take this integral, so that this is the integral over all positions and times of the vertices, when I fixed where the vertices are, it's in fact, I can sum all diagram topologies, all ways of connecting the dots with the Green's function lines. There's a factorial number of such diagrams. I can actually sum them very cheaply in n cubed steps, where n is the diagram order, if I represent them as a determinant of a matrix built on Green's functions. So we know that a huge achievement of determinants is that they can be evaluated in only polynomial number of steps, while the number of terms is actually factorial if we do it by the definition. However, this is not all, because if we do it this way, if we just take the determinant, then we also generate diagrams which are disconnected, which just basically fall apart, and they're pieces that are not connected by between each other by propagator lines. And these diagrams are not allowed in intensive quantities, and therefore we need to subtract all those disconnected diagrams, and this is where it becomes slightly trickier and slightly more costly. But it still takes only an exponential number of steps, which is an advantage over factorial sum. So then, once we've evaluated this integral using these determinants, evaluation of determinant with subtraction of disconnected diagrams, we can sample over all positions of internal variable vertices and their times by Monte Carlo. That's the algorithm. So when we apply it, typically this is what we obtain. So here I show a partial sum is a function of inverse diagram order. And you see that the partial sum looks completely meaningless. It blows up quite badly, and I cannot claim any answer. All right, so it seems bad, but actually it's not such a hard problem to deal with in this particular case, and it's actually well known in many-body theory that you can obtain the answer behind the series quite straightforwardly in a few steps. So the first step, you try to understand where the singularity is. I mean, what leads to divergence of the series like this, and you can just look at the ratio test of consecutive series coefficients to obtain, and the ratio test in the limit of large diagram order with roughly converges somewhere here. So this is my rough estimate of where the singularity is that leads to the divergence. I can have a number. So from this, I understand that the picture behind the series is like this. So this is the complex plane of expansion, the complex plane of psi. And this is the value of psi equals 1. Sorry, the complex plane of the expansion parameter. This is psi equals 1 at which I need to evaluate the series. And this is the singularity that is closer than the physical value to the origin, which limits the convergence radius. So this red circle is the convergence radius. But I understand that the singularity is actually has nothing to do with this physical point. So if I could deform the complex plane so that the singularity becomes farther away than this physical value, then the series will be convergent. And that is the essence of the method of resummation by conformal map. So basically, I map my plane of the expansion parameter psi onto a new parameter w by an analytic function such that it maps 0 to 0. And I try to choose this function w so that in the w plane, whatever was on the negative side, on the negative part of the real axis, goes farther away from the real axis than the than the side on the right. Therefore, the convergence radius now includes the physical point, and the series converges, and this is what we see. This is what we see for the transformed series. The blue points show that the series indeed converges, and we can extract a highly accurate result from the divergent series. Now, in the last couple of slides, I will just show the some applications without going too much into the physics of these applications. But one of the problem, which has been a difficult problem, is the problem of the metal-to-insulator crossover in the half-field two-dimensional Hubbard model. The problem is essentially that in 2 dimensions, there's no phase transition, but because of the Merman-Wagner theorem. But what happens is, as you lower the temperature, the long-range antiferromagnetic correlations, at half filling. By half filling, I mean 1 fermion per lattice side. They become extremely long range. The correlation length grows exponentially, and the system becomes, at some point, an insulator. And this has been a very difficult problem to describe with finite size methods. Despite the absence of the sign problem at half filling, I should emphasize that at half filling, there's a magic symmetry that allows to avoid the sign problem for finite size method. But even despite this, the huge correlation length does not allow to solve this problem even qualitatively accurately with finite size methods. But this is the problem, the perfect problem for diagrammatic Monte Carlo that work directly in the thermodynamic limit, and we can map out the phase diagram. I'm not going to go into details of this. I'll just refer to these publications for details, but I just say that it's quite a non-trivial problem how a metal turns into an insulator. There's an intermediate partially gapped or so-called pseudo-gap state. And the final example, I just wanted to go to 3D just to demonstrate that in 3 dimensions, we do have a phase transition. There's a new antiferromagnetic transition. And diagrammatic Monte Carlo actually allows to detect and characterize the phase transition working from the normal phase. It's actually quite simple because we understand that at the phase transition, for example, the susceptibility becomes non-analytic at the critical point. It diverges, and therefore the series that we evaluate at the thermodynamic limit must diverge in a particular way, which we actually know, and therefore we can extract the critical point from the behavior of the coefficients. And if we do it at half filling, 1 fermion per lattice side, where other methods work, there's no sign problem, we see that, well, at high temperatures, this is our results in some previous papers using finite size methods, that finite size methods work actually quite well. We start gaining some advantage at lower temperatures. But then if we go to the doped case, if we dope the system, if we change the density away from half filling, then all of a sudden finite size methods get the sign problem. They cannot extrapolate to the correlation lengths necessary to capture the phase transition. But in diagrammatic Monte Carlo, the method is actually quite accurate, and you can find the boundary between the normal and the antiferromagnetic phase. So I just want to thank my collaborators, internal collaborators, my postdoc Aram, former PhD student Feder, who is now in Paris, and PhD student Connor, and external collaborators, James, Eugene, Nikolai, and Boris. And I'll just leave you with this slide, which just demonstrates that over the last several years, the applications of diagrammatic Monte Carlo, the range of applications, the scope of applications has truly exploded. And in this conference, we have several talks on different applications, which go in much more technical detail. And I would like to encourage you to attend this and learn some more about diagrammatic Monte Carlo. Thank you very much.